Today's lecture is just going to be the continuation of what we talked about last week. That's the topic of diodes and how they behave in circuits, and in particular this quite important example of using diodes as rectifiers or to build a rectifier circuit and then putting them together with a few other elements to see how we can build stages toward having a DC power supply, a DC voltage source. And that's basically something that has as its input an AC signal, something, let's say, that you take out of the power supply, out of the wall plug, and then you convert it to an AC circuit. So what I'd like to do is to start by a brief reminder overview of rectification and filtering, which is what we did last time, and add a few small things on top of that, and then hopefully spend a good chunk of the time talking also about regulation. And something that comes together with that is the usage of Zener diodes. Now, as far as circuit level analysis is concerned, Zener diodes are not really that different from regular diodes. The main difference is that typically they are used for their reverse characteristics in the breakdown mode rather than their forward characteristics. But we'll look at that in detail. So let's do a quick review of rectification and that simple circuit that we started with last time, rectification and filtering. And this is the circuit we looked at last time. We have an AC source of voltage. This is how I've defined the polarity, Vn. And the goal was to deliver a DC voltage across this load resistor. Let me put this here. Call this V out. And we saw that the diode did the rectification for us, and we added a capacitor here to smooth out the variations that you see on the output. So that would be a smoothing capacitor. And this activity, we called it filtering, and we briefly talked about why that is. And this is what we saw for the characteristics. So if this is voltage as a function of time, and if my input was this sinusoidal signal, or in this particular case, a cosine signal, so if this is my V in, as a function of time, we analyzed the circuit in detail, and we saw that the behavior for the output will be essentially like this, that the output rises with the charging of the capacitor during part of the cycle, and then it goes down as the capacitor discharges into the load resistor when the diode is off. And this is the parts of the cycle that we saw this thing happening during. So this is basically continuing. So let me make sure this is clear. This is when the diode was on or conducting. And this is when it was off. And so if we look at the circuit, this is what really was happening. When the diode is on, this is the path that the current takes. And so you essentially have accumulation of positive charge on the top side of the capacitor, on the top plate. And so the voltage across the capacitor rises. And the voltage across the resistor is the same as that across the capacitor. Now, it's important to keep in mind, as this is happening, you have this output voltage on the resistor also. So there is a current also going through the resistor. So it's not just the capacitor. There is also current going through the resistor. So, and you have the KCL there. So the diode current is being divided into a current that charges the capacitor up. And the current in the capacitor is proportional to the rate of change of the capacitor voltage. And then there's the current that goes through the resistor. It's simply proportional to the voltage itself. So you have those two currents. And this is when it's charging. Okay? Maybe I'll indicate this with a different color here. When the diode is off, what happens? So after the capacitor voltage or the output voltage has reached its maximum and the input voltage starts to descend, now if we didn't have the diode there, the capacitor would just follow the input. But for that to happen, for the capacitor voltage to keep going down, it needs to send the current the other way around. And that can't go through the diode. The diode will allow the current to go only in one direction. So the diode then turns off. And the basically now you have a circuit effectively where the capacitor and resistor are still connected, as you would expect, but they're effectively isolated from the input. There's no path going back through the diode. Now what happens? You have a capacitor that's charged, and there is a resistor in parallel with it. You will have a discharge in the resistor. So this is when the diode is off. So diode off. So this is, sorry. And we quantified all these things last time, how much that drop of voltage is during each cycle that we called ripple. And we came up with some approximate expressions for it, an approximate expression for it. We talked about how long that interval is when the diode is on during the cycle, and a few other things like the average output voltage and current. So we did a quantitative analysis of this. Okay. Now, I ask you guys to think about something that you might say is a secondary effect, and that's right here. Right here. My question was, does it really look like an exponential decay from the very beginning? Does that behavior starts right at the moment of, let's say on this axis at t equals 0? Or is there something to think about a little bit about what happens during that transition from the diode being on and the capacitor charging and then starting to turn off? Did anyone get a chance to think about this? Okay, so it's something good to think about and talk about. No? And I don't want to go too much into detail because I'd like you guys to think about it on your own. But here's what I mean. If I zoom in, okay? If I zoom in near the peak, so this is where we have that peak of that input voltage. And then I have the output voltage going up with the input. And now that the input is going down, I see that the output is going to start a decay, an exponential RC type decay into the resistor. So is this how things happen? And is this curve really exponential of minus t over RC? Let's say with a peak value VP. Or do I need to think a little more if I want it to be really accurate? Is there something there to think about? Also, I think you would agree that the case I've shown here is quite exaggerated, right? This represents a very slow decay. So this corresponds to a very large time constant, RC, compared to the period of the signal, right? What if I had a small RC? So maybe this wasn't a very well-designed filter, so the RC drop was the RC drop was fast. RC was small, and things were like this. Yeah.
Judging from what we saw in the lab, I think we followed the curve more, and then followed the input more.
So if this was the curve going on like that, if this is what my RC drop at the output dictates, am I really going to see this? So if this is my output, V out, while this is my V in, can this take place on this circuit if the diode is ideal? It can't, right? Because V in is greater than V out. So if I were trying to impose such a condition, the diode would actually turn on because you're trying to enforce a positive voltage across it. And the diode would not allow that. Think about the characteristics of an ideal diode. So that diode actually would turn on sooner than allow this to happen. And if the diode is on, then the output would be going down like this. Or maybe I should use the other color. Right? So what is happening there? Physically, what's happening? So the output would be going down like this, at least for some time. If the output is following the diode, and which means the capacitor voltage is going down, which means the capacitor is discharging, it's losing some of its charge, does it mean then that there is a reverse current in the diode? No. So then what's happening? Well, the capacitor would have to discharge for this to go down. And there's no way for the current to go back through the diode in reverse. So the capacitor is actually still discharging in the resistor, but just not as fast as it would have had it been sitting alone together with the resistor only, right? It means that the capacitor and resistor combination are acting, have a response time that's fast enough so that they can still follow the variations on the input. Okay? So they can follow that for some time until the point at which the input wants to go down faster than that RC decay would have allowed. Okay? Or we should really talk about now a new RC starting from here. So basically, this would keep going for some time until the RC decay can become becomes slow enough compared to the rate at which the input is going down. And it can't follow it anymore. And then that's when the diode disconnects. So one good exercise to do is to try to estimate when this happens during the cycle. Now you see I have kind of exaggerated, I've zoomed in to the top here, right? But I sort of, by the analysis I did last time, when I neglected this, I implied essentially that that's a small duration of time. Okay, so it would be a very good exercise. So try to estimate this time. Okay, this would be a very good exercise. So this is one thing I wanted to draw your attention to. And so again, I haven't done a full-blown solution here. I want you guys to think about it. So if the diode is off, I have, so the question is to maybe elaborate on this a little bit. If the diode is off, then the output is basically a capacitor with some charge in parallel with the resistor, right? So it would start decaying exponentially. You have a first-order differential equation to solve all the standard things, right? But imagine that the RC time constant of this decay is extremely fast. So this, as soon as the input changes a little bit, as soon as the input comes down from its peak value a tiny bit, that the output can follow it. Because this, if you didn't have the input, the output would have gone down this fast, right? So the output can actually follow the input very fast compared to the rate at which the input is changing. You see? So the output can actually respond to the variations of the input. And so what happens then is, imagine the output has gone down a little bit, right? And this is kind of a mental exercise because these things are all happening at once. But imagine the output has gone down just a little bit. Sorry, the input. The input has gone down just a little bit. The output will immediately have followed. Okay? So imagine in your mind a two-step process where the input goes down a little bit, waits there, the output decays, quote unquote, exponentially, and reaches the same value as the input. But now compress this to an extremely small period of time to the point that essentially these are happening at the same time, simultaneously. So the output will then follow the input up to a point where the rate of the variations at the input becomes so high. You see, this is a cosine curve, and its derivative keeps becoming more and more negative. The rate of change becomes so high that the output cannot follow anymore because the output decay is too slow for that. And that's when they branch off. They separate. And then the input will keep going down, the diode becomes off, and the output will now go down at its own natural rate, which is the exponential decay. Okay. But if you have a well-designed rectifier and filter circuit in which the output variations are very slow, you have a large time constant, you are more like the case that I have drawn up here. And this thing will be just a tiny, tiny portion at the beginning. Okay. So that's what I'm hoping that you guys could work on a little bit to see if you can quantify it. Come up with an expression. Okay. So this is one thing. The other thing is, for the, and I'm happy to talk about this more, but I think there won't be much value unless you guys spend a fair amount of time thinking about it on your own. So we can revisit this next time or next week once enough people raise their hand when I ask who's thought about it. Okay. Then we'll revisit this. But so another question. What if my diode is not ideal? How, well, first of all, qualitatively, how does the behavior of the circuit change? If I have a real diode, not an ideal diode, So something that has that exponential voltage current relationship or dependence of current on voltage. So it has the real characteristics. Qualitatively, how does the behavior of the circuit change? If the diode is not ideal, let's start going through those different models of the diode that we had. We had the super simple one. In the forward mode, there was 0 voltage drop. It didn't take any voltage across the diode, and it could allow any positive current. Right? That's what we used here. But what if we went to the next level of sophistication? When we modeled the diode in the forward mode, not with a 0 voltage drop, but with something a little more realistic, maybe 0.5 volts, 0.7 volts, depending on the component that you have. So what if the diode required a 0.7 volt drop in forward mode? Then how would the output change? So I still have the same input voltage, this cosine curve. Well, if the diode is not ideal, here, let me draw this here to have it accessible. So this is my Vn as a function of time. If the diode takes 0.7 volts across it in the forward direction when it's on, during the time when the diode is on, what is the difference between the input and output voltages? 0.7 volts, right? Just think about your KVL going around the big loop. Minus Vin plus Vd plus V out equals 0. Okay? So if the diode requires a 0.7 volts, you see that V in minus V out has to be 0.7 volts. And that's what you see. V out is V in minus Vd. So this could be approximately 0.7 volts. And so your V out then would not follow V in, but it would be 0.7 voltage below it. So it would be more like this. Now again, maybe I'm exaggerating a bit. Okay, so this difference is approximately 0.7 volts on the vertical axis. So this is something that you could verify in the lab. I think some of you said you have seen it have a difference. And did you measure it? No. So maybe next time measure it. See how much it is, right? It will give you a sense of how much the diode takes in the forward region. Now let's make the diode one step more sophisticated, because we know that the real diode does not have a constant 0.7 volt across it when it's on, but its voltage, its current actually changes with the voltage. Now a very small change in the voltage will lead to some significant change in the current. So if we look at the different models for the diode, starting with the very simple one that is our ideal diode. This was the first one. And then this is the other one that we just used. Or I can just call this 0.7 volts. But what if we try to make it one step more realistic? So maybe something that goes like this. It's pretty steep. So for a large change in current, you need very little variation in voltage. But nonetheless, there are some variations. If you factor that in, then the output curve will not be a constant 0.7 below the input. The difference between input and output will be changing throughout that conduction region. It will go maybe somewhere between 0.65 and 0.73, just to throw some numbers. Because the diode current is changing as you charge this capacitor at different rates. And so the voltage that it will take, according to this, if the current is changing, well, the voltage is also changing a little bit. What if you made it even more sophisticated? So you had an actual exponential behavior for the diode, or maybe this is too exaggerated, something like this, right? So same thing. Again, the current and voltage have a kind of non-trivial relationship. And as you go through this cycle, the charging part of the curve, as the current changes, because the rate at which you're charging the capacitor changes, the voltage across the diode also changes. And so this curve, this blue curve, will be, during that whole charging part, will be slightly shifted with respect to the black curve. And that would be a value somewhere around 0.6, 0.7. And it would be varying. Now, is this a problem? Well, depends. So not only are you losing a little bit of the input voltage, but there's also some additional distortion introduced to it. So the output is not a simple cosine minus a constant during that time. It's a cosine minus some value that's itself varying. And so you have some distortion there, but that's fine. This is life. And we are dealing with nonlinear elements, and in general, as soon as you change things a little bit to an electronic circuit, you start having distortion. That's fine. The question is how much you can tolerate. So imagine if you had an input voltage that was maybe 20 volts. Maybe you wouldn't care about 0.7. But if your input was 1 volt, then this would represent a significant chunk of the input that's being taken away. So this is something else to think about. Again, another very good exercise would be to try to model this accurately, actually calculate this. And in these additional problem sets that I've posted, which I emailed you about, I have given you an exercise about how to, which involves modeling the current voltage in a circuit with an actual diode that has exponential characteristics. You need to write a small code, and I'll post the solutions for it too. But it would be very nice if you could try it on your own. And then, based on that, you can extend it quite easily, I think, to doing this accurately. These are the kind of things that are sort of maybe second-order effects, you would say, not the basic operation of the circuit as far as the general concepts go, but to gain really good insight and understand these and feel these elements, these would be excellent exercises to do. Okay, and I'm happy to talk about them more again if there is a number of you who will try it and have interest. But at least as a first degree correction, recall that the output is going to take a little bit of the input for the diode. So let me just say that this is approximate. Okay. I actually wanted to also briefly introduce the transformer, which is something that you would encounter if you really actually were to build a small power supply, a DC power supply, a DC voltage source in your lab. because imagine you have the output at the wall, which is, depending where you are, but here, 110 volts, right? And that's an AC signal. If you wanted to build a DC source with an output of 5 volts or 9 volts, then, well, this would give you an output way up there, in the 100 volts range. So you would want to actually first scale down the voltage using a transformer. So maybe I'll just briefly introduce a transformer. So it's basically 2 coils like this. So if this is, or let's just call it V1, V2. And you might indicate the polarities like this, or sometimes they put a dot there to indicate which way the polarities are. In this case, they're both in the same direction. And so if these two are coupled, and if the first one has N1 turns, and the second one has N2 turns, then the ratio of the AC voltages is equal to the ratio of the turns. Has anyone used a transformer here? No? Yeah. So if you build a power supply, you'll likely use one. But it's basically, has anyone seen a picture or knows what it roughly looks like? You will find them all over the place, right? It's basically coils, magnetically coupled. So sometimes they show it, I think, like this. Now, this sounds maybe a little strange at first, because if I can, so now imagine if N2 is greater than N1, I can just scale up my input voltage. Does that violate conservation of energy and power in this case, if I do this over time? So I have an input of 10 volts, let's say AC, and I have a transformer that has 10 windings at the input on the input side and 1,000 windings on the output side. So then I'll get 1,000 volts on the output, just like that. Sounds too good to be true? So this would help with what you're asking about. You don't violate conservation of energy here, maybe unfortunately. Because the current on the output will be then correspondingly small. So the power at the input and output will be the same. Okay? So you go up in voltage, go down in current. So you have to have enough power capacity to get what you want. Yes. But so this is something that you will see. And if you wanted to build a power supply, you would see typically, let's say you have your input at the wall, then a transformer, then your diode and resistor and capacitor. Okay. So maybe here. So the circuit might look like this. So you have your V in. You feed it to this transformer. Then you put your diode here, and then your capacitor and load.
But wouldn't the current jump side, in theory at least, only depend on the load, the resistance, and then basically adding more voltage with the same resistance?
Yeah, so it's a very good question. So wouldn't the current on the other side be determined by whatever load is connected? So if I have, let's say I have the transformer here, and I have just put a resistor in parallel here, and then the current is dictated by that resistor, right? So if that requires a very high current, that means the transformer will not be able to do its job, right? Unless you feed it more current at the input. right? And that's why if you feed it enough power, as long as the losses in it won't get it too hot to the point that it will blow up. If you feed it enough current at the input, then you can feed your load at the output. So that's a design consideration. So this is the voltage, DC voltage, DC power supply with transformer. Okay. So let me write it down here. This is your half wave rectifier. Together with transformer. The transformer just helps scale the input voltage. To a desirable range. I hope through what we are doing here, you also see how we are kind of starting to look at things like blocks and adding them and getting functionalities, because this is essentially what electronics is. But as you add things, you have to always consider whether the stages that you add match. So, for instance, the question of power that we just discussed has to be taken into account. And by the way, I don't know if I actually explicitly mentioned this, but this is called half-wave rectifier because we are only using the positive side, half of the wave. So this is half-wave rectifier together with the transformer. The next thing I wanted to talk about, building very directly on these, is, well, why half-wave? Isn't it a shame that we are throwing away that half? So I want to draw a circuit that's a full-wave rectifier, and I want you guys to think about the analysis on your own for a few minutes. A full-wave rectifier. And I can include a transformer, again, if I wanted to. But why don't I include one to make it look nicer? Now think about what this circuit will do. Assuming I'm drawing it correctly, we'll verify. Can be a little confusing. So imagine I have a V in here, or that you're scaling down. Maybe let's call this V1, and then here, doesn't matter really. Better to call this V in, and then here call this V1. So the polarities are defined in the same direction. Imagine V in is a sinusoidal signal. Let's say a cosine like we had before. What is V out? Think about that for a moment. So if the turns are N1 and N2, then V1 is simply that. So I don't really have to worry about that. That's a simple scaling. So if this is my V1, so it's the scaled version of V in, what will the output look like? Say again? Yeah, so the output will actually take the negative side and invert it. So it will have the full cycle. Let's look at how this happens. So the analysis is very much similar to what we did before. You can start again by writing a KVL. Look at this, for instance. If I take this loop. Now, maybe this is a little intimidating because there are 4 diodes. And in principle, there could be 16 different possibilities for which one is on and which one is off in terms of combination, 16 different combinations that you have to take into account. So it takes a little bit of time to think about it and get a feel for what's happening. But think about, for instance, writing one of the KVLs. You could go like this, around this loop. So you have a voltage rise of V1 here. Then if you call this VD1, you have a voltage drop there. Then you have a voltage drop on the output. And like that. You see? And so, for instance, that's a KVL that tells you minus V1 plus VD1 plus Vout plus VD2 is equal to 0, whatever these values are. But that KVL holds. I've just followed a loop. Now, the way it's drawn, you have to maybe think in 3 dimensions because there's one wire going over the other. Or you can maybe bend things around in your mind. But that's what you're doing. You can write another KVL that uses the other diode. So you can go in the other direction using the other 2 diodes. Imagine for a second, now, rather than trying to consider all the 16 possibilities for every value of input voltage, because I've seen it before, let me maybe speed up the way we look at this. Imagine for a second if the input is at a positive point, if V1 is positive during the part of the cycle when V1 is positive, would things work out if diodes D1 and D2 were on? Let's see. Well, if the diode D1 and D2, if those 2 are on, and if they're ideal diodes, they take 0 volt forward voltage, then basically all it says is that Vout would be equal to V1. So that's pretty good. If that's the case, what's happening to the other 2 diodes? Let's call those VD3 and VD4. So think about the KVL going through VD4 and VD3 and the output. So I write that KVL with red, and hopefully this won't be too confusing. It will be a little confusing, and that's that. I hope you followed that pattern. But so if I do it like this, I'm getting another KVL that says minus V1 minus VD4 minus V out minus VD3 is 0. If you look at the first KVL, if the diodes D1 and D2 are on and V1 and VD2 are 0, V out will be equal to V1. Now, if V out is equal to V1, from the second equation, you will get the sum of VD3 and VD4 to be equal to minus 2V1. Now, if V1 is positive, the sum of those two diode voltages is going to be negative. And you can see that, and the situation is very symmetric. Basically, what happens is in the positive half of the cycle, D1 and D2 are on. V out is equal to the input, or the scaled input, V1. In the second half of the cycle, the reverse situation happens. V out becomes equal to minus V1, so this flips, and VD3 and VD4 become 0, and then VD1 and VD2 become negative. So now, again, this is something that will take a little bit of imagination and thinking about it. And so I don't want to take too much time to repeat it here, but hopefully you guys can also watch the video later on. But it's really important that you go through these paths and do these and see. So this is really what you want to look for. Convince yourself that, or show, when V1 is greater than 0, D1 and D2 are on. So VD1 equals 0 and VD2 equals 0. And by KVL, V out is simply V1. On the other hand, when V1 is less than 0, and I should also add here, and D3 and D4 are off. On the other hand, when V1 is less than 0, D3 and D4 are on. So VD3 equals 0 and VD4 equals 0. And by KVL, V out equals minus V1. And D1 and D2 are off. So this is really a matter of going through all the possibilities and making sure that basically you have found a consistent set of diodes on and off for every case of the input being either positive or negative. And these are the equations that guide you through it. Okay? That's what I've used down here. But it's really important that you go through this. Now, perhaps so these are the KVL equations, and I hope I've drawn things correctly, so go verify. But if we were to just draw the path for charge flow, the path for current in the two halves, this is how it would look. This is how it would look. In the positive half of the cycle, the current is flowing, or the charge rather is flowing like this. So it's the same as before. I've just added some arrow to show. And you see that the current is going in the forward direction of both D1 and D2. In the second half of the cycle, when V1 becomes negative, and V1 is negative, is that that voltage is reversed, then the current is going like this. So I'll again add the arrows. You see? Going down like this. So you see that the two other diodes are being used in the negative half, but the current is going still in the same direction in the load, in the output. And that's the beauty. That's what this circuit is accomplishing. So then your output will be, in the positive half, will be just V1. So this is your V out. In the negative half, it will be minus V1. And that's also V out. So you've flipped that side. So now you have a full wave rectifier. You haven't thrown out the negative side. What if we added a capacitor in parallel with the resistor? So if we said and filter, so if I add this capacitor in parallel, this is really, again, where you start building up on what you've seen before. The addition of this capacitor, the way it affects the circuit is no different from the way things happen in the half-wave rectifier. You're now filtering the output, except that the RC discharge that you see will not take most of one full cycle, but it will take most of a half cycle. So the output will then look like this. With the green, the output will look like this. Sorry. The green is V out if we also have a capacitor there. How would you analyze? How would you find the ripple and the conduction interval and so on? Very much the same way as you did before. And in fact, if you were to follow the same approximations, you might recall that for the discharge time, back then we said it's approximately one full cycle, where here it's approximately a half cycle. So you will get a factor of 2 difference in the equation, in the expression we came up with for the ripple. And similarly other things. So if the ripple is less, a little bit less, well, maybe that's something desirable. We've gotten a factor of 2 improvement. So the ripple is less. This is a full wave rectifier. And I want to draw one other version of this full wave rectifier. That's not a bridge like this, but full wave rectifier using a center tapped transformer. You can draw a wire from the middle of a transformer. So if this is your input, your output can be like this. You can put a diode here, and this is your load. Call this D1 and D2. And what happens here is that this transformer, you have not only, let's say, this V1 extracted, but also have V2 extracted. And if this wire is at the center, then V1 and V2 are the same. So they're just two, it's like two different AC voltage sources. And in the positive half of the cycle, you have this. In the negative half of the cycle, you have this. So again, you see that in both cases, you have the current going in the same direction in the output. So this is also a full wave rectifier. Is there any advantage for this circuit compared to the previous one that you guys can think of? There are 2 diodes instead of 4, but maybe I need a more sophisticated transformer. Right? So there's a trade-off. But one thing you could say maybe is that, you see here, what if the diodes were not ideal? If each of them wanted an approximately 0.7 volt drop? Well, the output would be 1.4 volts below the input, right? I would lose a total of 1.4 volts because I have 2 diodes worth of drops from the input to the output. Whereas in the other one, I'd have only 0.7 because I have 1 diode. Mm-hmm. Yeah, so we have an excellent question here. During the positive cycle, V2 is also a positive voltage equal to V1, right? So what problem does that create? Let me write the KVLs. Right? I've written the KVLs along those paths. So if V1 is positive and V2 is positive, the first equation will give you V out equal V1 if the diode is on, VD1 is 0. The second equation will give you VD2 equals minus V2 minus V out. And V out is the same as V2, same as V1 and V2. So the second diode is off. So that second diode is now off, and that prevents any interference from the lower half of the circuit. There's no current going there. On this note, I think maybe we could take a short break. OK, so I'd like to start a new but very related topic. It's not really, we are not going to introduce any new, really dramatically new concept here, but we're going to look at the application, another application for the diode. And we are going to, for this, mostly use the diode in the breakdown mode, in particular a Zener diode. But let me introduce the concept first. So this is called regulation. Well, look at what we have accomplished so far. What we have accomplished so far is we've taken an input that's a sinusoidal curve, and we have managed to turn it into something that has a substantial positive average with some fluctuations around it, some variations around it, that ripple. Now, that still is not terrific, right? Because if you wanted a DC voltage source, you wanted something maybe a little more constant than this. And what we mean by regulation is to take this green curve. It could be the output of a half wave or full wave rectifier, to take this and make it a lot more constant or a lot less strong in its variations. We want to regulate it. OK? Now, what is an ideal voltage regulator? Well, that's a theoretical voltage source, right? It will just give you a constant voltage, an ideal battery. What are the IV characteristics of a battery? What's the current voltage characteristics of an ideal battery? Yes? That's it, right? So let's say there's a 1.5 volt battery. No matter what the current is, the voltage is 1.5 volts. That's really what you would like to have, right? Well, if you had the ideal battery that you wanted, you wouldn't be trying to build a power supply, right? So you don't have that. We are trying to build something that mimics essentially a battery, right? And in fact, you would need something like that to even charge a battery starting from what you have from the power station. Well, if we don't have a battery, if we don't have an ideal voltage source like that, is there some element that you can think of that has IV characteristics that somewhat resemble this? And yeah, don't go too far, the diode, right? Because the diode was not a straight line like that, but maybe it was in some part, it was almost like a straight line. In forward, or if you went far enough in reverse, almost a straight line. Not for the full range of currents, but in forward, if you went to, and this is exaggerated, of course, the forward bias is small, but maybe if you went to 0.7 volts, you would get an almost straight line for voltages around 0.7. Or in reverse, if you went to, let's say, minus 5 volts, depending on the type of diode, you would get an almost straight vertical IV curve. So we are going to use this property of the diode to build a regulator, to create a circuit that will basically manage to keep the voltage somewhat constant, even despite some variations in the load current. Now, the forward regime, or the forward bias that you need on diodes is 0.5, 0.6, 0.7. You don't have a whole range there. So if you wanted a regulator that would give you a 10 volt voltage, this is not going to be helpful. But the reverse breakdown voltage is actually, you can get a whole range from a few volts to a few hundred volts in different components. And these are Zener diodes, diodes that have been made particularly so as to have a very sharp and straight vertical descent at some well-defined negative voltage, and to operate in that breakdown mode. And so that's what we are going to look at. Okay, so that's not to say you can't do regulation with regular diodes, but Zener diodes have been made to particularly have good characteristics there. Okay, so I'd like to start by a simple problem here. Consider this circuit. And this is really an example of solving a diode circuit. Okay, it's not really, you're not introducing new fundamental concepts. So let's do an example of a diode circuit. Consider this circuit. Let's call this V1. Let's call this R and this R1. Okay? Assume the diode has these characteristics. I'm doing a somewhat idealized so straight line there at 0.7 volts and straight line here, let's say at minus 10 volts. Perfectly vertical. Okay. And let's put numbers here. So imagine V1 is 15 volts. And R1 is 10 ohms. And the load here is 1 kilo ohm. And this is V out. This is an example of a diode circuit. Solve this circuit. Take a few minutes, think about it on your own. What is V out? I'll give you a hint. What is, well, you're trying to solve an extremely simple circuit. It has 3 elements, one of which is the diode, and you might feel intimidated by that. Remember, the diode can be, look at the characteristics, it can do only one of a few things. It can either have a 0.7 volt forward voltage, and that would require a positive current, any positive current, right? It can have 0 current as long as its voltage is between 0.7 positive and minus 10. And it can have a fixed minus 10 volt as long as its current is negative. So you just have to try these 3 possibilities of where the diode is on its characteristics. And let's imagine for a second that the diode is at its 0.7 volt positive. Let's see if things work out. So if I have 0.7 positive, like this, let's solve the rest of the circuit. What will be the voltage across the 10 ohm resistor? $15.7 volts, right? There will be a current going there, 1.57 amps. What's V out? Is minus 0.7. And so there is a current going like this, 0.7 milliamps. What does KCL here say? That you have a current going like this of 15.70, sorry, 1.577 amps. Can the diode allow that reverse current like that? No. So this doesn't work. So if I started by assuming that the diode was on at 0.7 volts, I would reach a contradiction here. So contradiction. So the diode is not on. Well, let's try another possibility. Let's see if it can be at the minus 10 volts. Or if not, then maybe it's somewhere in between. Right? Let's try the minus 10 volts. So I'll erase all of these. Maybe I have to be a little more efficient here.
Wait, so why is it a contradiction?
Because the diode, why is it a contradiction? Because the diode does not allow current in that direction. So that doesn't work. What if we assume that the diode is in the breakdown mode, minus 10 volts? Let's try that. So if it's minus 10 volts, it means we have 10 volts like this. Then what is the voltage across the resistor? By KVL, that's 5 volts. So here I have 0.5 amps. My V out, which is the same as the diode voltage, is 10 volts. And so here I have 10 milliamps. And what is the diode current? By KCL here is 0.510 amp. Is that allowed, or is that a contradiction? A reverse current of 0.51 amp. Well, let's look at the IV characteristics. If the diode has 10 volts negative here, can it have a reverse current of 0.51 amps? Yeah, so it would be somewhere here, let's say. So no contradiction there. That is the solution to the circuit. Oh, sorry, my mistake. You're right. It should be 0.49, not 0.51. Thank you. Yeah, my mistake. 0.49. So you are on this point, on the IV characteristics, no problem. And that is the solution to the circuit. Isn't that nice? Look at the input. You have an input voltage of 15 volts, and your output voltage is how much? 10 volts. Now, what if my input voltage was 14 volts? What would the output be? Solve this on your own. Now solve the same thing. Assume that instead of 15 volts, you have 14 volts at the input. Calculate the output.
Are you still taking the diode as -10?
Same diode. Same diode characteristics. The only thing I've changed is the input voltage. Instead of 15 volts, I have 14 volts. Well, let's solve it. So this was 10 ohm. Same diode. So let's see. With the insight I have from the previous circuit, maybe I'll start with the guess of maybe the output is, again, in that range of the diode breakdown. Let's see if that works out. So if I assume that the diode, again, has a 10-volt reverse voltage like that, which means the output voltage is 10 volts. Those are just in parallel. But what do I have here? I'll get a 4-volt drop here, which means this current is 0.4 amps. What is this current? I have 10 volts over 1 kilo ohm. That's still 10 milliamps like before. What is this current? Are things consistent? Is the diode happy? Yeah, it's here. It's at a different current, minus 0.39 amps, but it has the same voltage of 10 volts. And I found the consistent solution. Again, in the circuit, if I assume that it was on, if it was forward, I'd have a 0.7. I would get the same contradiction that I got last time. So this circuit gave you the same exact output voltage, even though the input changed from 15 to 14 volts. Yeah, so I think the question is, we said the diode could be on or off, right, before, 2 possibilities. That was a diode when you were not thinking about the breakdown mode, right? So this horizontal line continued until minus infinity, basically, if you didn't have this, right? So the IV characteristics only had two regimes, if you want, the on part and the off part. Here there's a third possibility, that it's on in the reverse mode, if you want. This is called breakdown, as we mentioned. So you have to consider 3 possibilities, this, or that. Right? But it's the same approach. And because I kind of knew which one was the answer, I started with that one. But you can go ahead and see that the other ones lead to contradictions like we did in the previous example.
So we have one more case of the 0 that we didn't write out.
It's a case of not 0, but a negative voltage and any negative current, right? And that's what we got. A negative voltage, you see the polarity is reverse on the diode, and a current going in the reverse direction, right? So a reverse voltage and a reverse current. And that's operating in the breakdown mode. So in both of these cases, in both of the above cases, the diode is actually operating in the breakdown region. Reverse voltage and reverse current. What if the input was 13 volts instead of 14 volts? Same thing. But you would have, instead of 0.4, up here you would have 0.3 amps, and the current going through the diode would become 0.29. And so on and so forth. What if the input was 8 volts? What do you think would happen then, without doing an analysis? But again, that would be something that you could take a look at on your own. If the input was 8 volts, then would the output be minus 10? Sorry, 10, the way. It wouldn't. So if the input was below a certain value, the output would not be able to be kept at 10 volts. The diode would not be able to maintain this 10 volt reverse. And that's, again, something that comes from the KVLs and KCLs in the circuit. So it's not a new, there's no new basic concept here. It's just an example. So please, at home, go try to solve this for a few different values of input as well as a few different values of those resistances. For instance, let me throw another example. What if, so I keep the input at 14 volts, but in terms of, instead of the 10 ohm resistance, I put in a mega ohm. What would happen? So same problem as what you have on the page here, but the 10 ohm resistor has been changed to a 1 mega ohm resistor. 1 mega ohm, yeah. So I still have 1 kilo ohm here, but I put 1 mega ohm here. Let's see what happens. Let's assume that the same thing works as before. So I have 10 volts here. Let's be optimistic, which is 10 volts here. So here I have 4 volts, which means how much current do I have here? 4 microamps. 4 microamps. And here I have 10 milliamps as before. What is this current? Four microamps minus 10 milliamps. That's a negative value. So that means the current is really the other way. So it means you need the 10 volt reverse on the diode, but a current in the forward direction. That contradicts this curve. You can have your 10 volt reverse, that's fine, but that would require a reverse current, not a forward current. So this contradicts the diode being in breakdown. Because the current is actually the other way, you might say. So it's actually 10 milliamps minus 4 microamps in that direction, which is in contradiction with the diode being in breakdown. Okay? So you start seeing some patterns here. Okay? And these are some examples of regulator design. What you just saw was a regulator circuit. Regardless of whether the input was 15 volts or 14 volts, the output was held at a pretty nice fixed 10 volts. Well, so if you had built a rectifier and a filter that gave you an output that had the ripple, an output that was swinging between 14 and 15 volts, and then you put this circuit after that output, then you would regulate it to 10 volts. Right? But you see that there are some things to be considered. For instance, what is the value of this resistor? If it was 10 ohms, it worked. If it was 1 mega ohm, it didn't. So go through the circuit again. Like I said, play with a few different values of input and those resistors to see how things change. this is the essence of regulator design. We will take a slightly more advanced look at it next time by looking at a diode that has not this perfect straight vertical line, but a more realistic line. And by the way, the diodes that are used in this, like I said, are Zener diodes. So you will see typically that they have a wiggly thing here on their symbol. So we will introduce that next time. That's it for today. Thank you.